رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, I'm just going to go over how to get the graphs for the MATLAB coursework, DEN5200 on control systems. Everything in this video will be based on that which was delivered in the MATLAB sessions by a TA. So this isn't any sort of plagiarism or anything. You can be assured that all of this stuff was from the MATLAB sessions delivered by the TAs. So let's get started. I'm not going to explain much of the theory, just bits here and there. I'm literally just going to go over what to type, how to get the graphs, which graphs to get, stuff like that. So open up MATLAB. Once you've opened up MATLAB, make sure you save your file with a name that has no spaces in the name. If it has spaces in the name, then it won't run properly. So the first thing we have to do is define the mass of the system. Whenever you start a line in MATLAB with a percentage sign, it makes it green. That means that line won't be part of your code. That's just a note. That's literally just a note for you to, know where you are. So let's start off by defining the mass of the system as 1.1 kilograms, which is what they gave in the lab handout. Then the next thing we have to do is define the parameters KD and KP. So what are these parameters? These parameters, if you read this lab handout and read the page previous, you'll see that this has something to do with the PD controller. So just read it and find out what it's all about. But in the instructions, in the procedure, it tells you that KP and KD are constants between these two ranges that you have to choose, and based on the choices you make for these, based on the combination, you have to generate graphs of the response of the system, and then you have to change these values, trial and error, until you get a system with a response that satisfies the performance criteria, the requirements. So let's start by putting in any old values for KD and KP between these ranges. Let's pick, for instance, KP equals 0.5, KD equals 3. Okay, now what we have to do, now that we have chosen some numbers, we have to get ready to plot the system's response. So how do we model the system here? The model of the system is given to us in the previous page. This is the model of the closed loop system. That's the diagram of it. This bit here is the PD controller. That's the system itself. The PD controller looks at the error, so how far the system is away from the targeted set point, and then it feeds some information, some instructions to the system in an effort to try and get it to X, which is the desired set point. So anyway, this is the model of that, basically. GCL, that's what they've called it. It's a closed loop, CL, closed loop transfer function. And inside here, these constants are present in this equation. KD and KP, they're the governing constants of this whole thing. So we now have to model this system in MATLAB. Whenever you model a system of a transfer function in MATLAB, you have to type it in there. I'll show you what the code is. You have to type it in there as the coefficients of S. So anything with an S or without an S, you look at those as coefficients, the same way you treat coefficients of any other, like a quadratic graph or whatever. So we type in the coefficients in here. So let's start GCL. Let's define it as a transfer function, TF. That's how you begin with it. Open bracket. Then we're going to have the top of the fraction, comma, the bottom of the fraction. Something's going to go inside these square brackets, then close brackets. So in the top we type in the coefficients of this transfer function. KD is a coefficient, KP is a coefficient. So we type in here KD, KP. Make sure you do it in the right order and make sure that you use the same spelling and everything as you've used right here. So the bottom now, M, KD, KP. M space KD space KP. So what is that? That is a that is the transfer function of the first system, because there's two systems in this coursework. So that's the transfer function of the first system. Now we've got to draw the graph like they said in step 1. Draw, plot, step response graphs of the closed loop system. So how do we do that? Type in LTI view. LTI view is a command in MATLAB that allows you to view graphs basically. Type in that, some apostrophes, and inside the apostrophes the word step. That means you want to see a step response graph, as they mention in the coursework brief. So the step response graph of which system? Put a comma and type in the name of the system, which is GCL. Close brackets. That, what we've just done, is step 1. I like to label everything like this with percentage signs. That makes sure that helps you make sure that you when you read it back, you know what each bit of code is doing and what each thing is about. So that's our first our first combination of KP and KD ready. So let's run this now. Here we go. So after running this, it's given us this this nice graph over here. Let's full screen it. Once you full screen it, go to characteristics, peak response, settling time, rise time. Read the lab handout to find out what each of these mean. So I'm going to click on the dots. That will allow you to bring up these labels, and these labels will tell you the overshoot, the rise time, and the settling time. In the lab handout you will see that there's a set of requirements that the system must satisfy. Here it is on page 4. The rise time must be less than 0.5. The rise time in this combination of KD and KP is more than 0.5, so it doesn't satisfy. The second criteria, percentage overshoot less than 5%, settling time less than 5 seconds. The overshoot does seem to satisfy, it's under 5%, but the settling time for this combination of KD and KP does not satisfy. So that's the first one. What you've got to do is save this as a picture. So let's go to print to figure. File, print to figure. That will allow you to save it. What you should do is go to insert a text box, and inside the text box put in the parameters that you just chose for this one. So what was it? 0.5 it was, I think, and KD we chose was 3, I think. Yeah, that should be okay. So there's my text box, there's the label of this graph, you can move it around. Now let's go to save as. Over here, pick one of the picture formats. So I like PNG, or there's JPEG down here somewhere, TIFF. So just pick a picture format, PNG. Let's make a new folder. Called MATLAB pictures. and the name I would like to save it as is 2, come on, not 2, sorry, 1A. I'm saving it as 1A because 1, I'm matching it with the name of the step, and A because I'm gonna save a few more of these in a second, up to 5 of these it says. So let's call it 1A, save it in there, and that's saved. Okay, now I can close this one as well. Now change these values around. So let's, instead of 3, let's put 4 over there, and instead of 0.5 let's put 0.6, and now let's try it again and see if we can get it to satisfy those criteria. So run it again. Alright, full screen this thing. Characteristics, peak response, characteristics, settling time, right click, characteristics, rise time. Those were all right clicks, by the way. Then get these boxes back by clicking on each of the dots. Right, what do we have now? Now the rise time, it's become closer. It's become closer to 0.5, the acceptable range, than it was. The overshoot has also come down, and the settling time has come down. Okay, so the values we chose are a step in the right direction. So in that case, let's save this as well. Save this as another print to figure, full screen, add a text box. For this one, KP was 0.6 and KD was 4. Put that there. Save it as a PNG, as in the desktop MATLAB pictures. Let's call it 1B. Save that. Then you can close this, and like that, keep going, keep changing these numbers through trial and error, and try and get towards satisfying of those criteria. And once you have done that, put all of those values in a table, make it look nice, of your KD and KP combination, along with the 3, the settling time, the rise time, and the other one, the overshoot. Excuse me. Put all of those in a table, make it look nice, and you can put that in your coursework. So I'm going to skip the next few because it says you can save up to 5 of those. And now I'm going to move on to step 2. Find the values of KP and KD in the range given above, so that the closed loop system satisfies the performance requirements. So step 1 was trying to get towards satisfying them. Step 2 is saying, okay, now actually find which values satisfy the requirements, save them, draw a step response graph, and put that in your report. So I did this before, and I found that for me 0.65 and 4.39 worked quite well. I think a few other numbers also work, so you don't have to use the exact same ones. Try it yourself and get some numbers that work for you. It might be somewhere, it'll probably be somewhere around here. So if you see now, if I run this, full screen it, right click, peak response, right click, settling time, right click, rise time. Okay, so the rise time is under 0.5, just under. Overshoot is under 5%, great. Settling time is under 5 seconds, so this definitely satisfies the thing. So now I'm going to go print to figure. I'm going to save it, desktop. You have to do this every time, you can't just select a thing and leave it. This is called 2. I'm going to call this 2 because it corresponds with step 2. And I'm going to save it with that name. I can close this, close the other one, go back to MATLAB, and now I can change the name of that to step 2 to show that I'm up to step 2, up to here. So now we've done that. That's the end of the whole of the first system. Now we're onto the next system, the notch filter system. We've got another system. This system is more complex. It has more weight, therefore more vibrations and more resonance. So first what we've got to do is model the system, see how it looks without the notch filter. Then we've got to design a notch filter and try and bring down the resonance. So first we have to design this system without a notch filter. So what does this system look like? Figure 7 shows a representation of the system. This is a block diagram. It's showing it has 3 parts, CS, HS and GS, and they're arranged in this way. These two are in a loop, and then the loop is in series with GS. So step 6 is telling us to basically work out this thing, work out a transfer function for this thing, a transfer function that represents figure 7. So how do we do this? We've been given 3 separate transfer functions. We have to put them together. CS was given to us on the previous page, on page 4. CS is KDS plus KP. HS is given to us right here, and GS is also given to us right here. So we have to put these into MATLAB. We have to define these in MATLAB. That's our next step. And then we'll use MATLAB to put them together in this arrangement. So let's put those into MATLAB first. So I'm going to put a note saying that we are now defining CS, GS, and HS. CS equals something, GS equals something, HS equals something. So what are these? CS is that right there. So what we've got to type into MATLAB are the coefficients. Just like we did for the first system, we typed in coefficients. Over here we're going to type in coefficients as well. So the coefficients, the highest order thing here is the thing next to the S, and then the thing without an S. So KD is first and KP is second. So let's type that into MATLAB. So remember how we did it? TF, open bracket, top of the fraction, comma, bottom of the fraction, close bracket. In the top, we said first goes KP, no, KD, yes, KD, because that has the highest order, then KP. On the bottom of the fraction, we just put a 1, because it's just over 1. Now, GS. GS is a transfer function. Open bracket, top of fraction, bottom, close bracket. Inside the top, we put the coefficients 5 and 20. And in the bottom, we put the coefficients over here. They will be multiplied, so there will be an S4 term with a coefficient 0.1, an S3 term coefficient 5.5, and an S2 term coefficient 22. Then there will be no coefficient for the S term, and there will be no coefficient for the term without an S. So 0.1, 5.5, 22, 0, 0. That's what it will look like. So 0.1, 5.5, 22, 0, 0. Great. Now HS is a transfer function, open brackets, top of fraction, bottom of fraction, close brackets. In the top, there's 1, 5 and 20. And in the bottom, this will be multiplied in the same way, and I believe that's the same, so it will be 0.1, 5.5, 22, 0, 0. the same. Copy, paste. Okay, so now we've defined these three transfer functions, CS, GS, and HS. Now, how do we put them in this arrangement as shown in figure 7? Let's start by doing the loop first. So let's call the loop fig7 loop. Fig7 loop. Let me just put a note. Let me just put a note above it saying that what we're doing now is the loop. Fig7 loop. Let's use this command here, feedback command. There, feedback CS, HS. What that means is CS and HS are in a loop, in a feedback loop, and they're arranged like this. CS is first and HS is next. That's what that has just done. Now, after we've done that, let's put the loop in series with GS. So let's call that fig7 CL. CL, the closed loop transfer function of figure 7, is going to be series, open bracket, fig7 loop is first, in series with GS. There we go. Now what we have to do is we have to run this. We have to run this because we're going to try and find out what the transfer function that we've just achieved actually looks like, because we have to write that down. That's what it tells us to do. So let's run it. Okay, the graph that's just popped up is the previous one right there. So that doesn't matter to us because we've already got that. And what I should have done is put a % sign in front of it so that graph doesn't keep popping up. Anyway, what we did that for, that running, was for this thing here in the command window. Scroll up a tiny bit until you can see fig7cl over here. This is the transfer function. That's what it actually looks like. That's what this series fig7 loop GS actually looks like in numbers. So copy that, go to Notepad, paste it, and save that, and call it 6. The reason you can call it 6 is because that's from step 6. That makes sense. Save. Now what we have to do is we have to modify this transfer function. As you can see, it's in the order of 8s and 6s and 7s. Very big, very high order. We've got to reduce the order, because if we reduce the order, the graph that we generate, MATLAB will allow us to, see the performance values. Otherwise, in the current state, if you drew a graph now, you wouldn't see, MATLAB wouldn't show you the performance values. It would show you the graph, but the performance values wouldn't display properly. It would say NA or something like that. So let's modify it. The way we modify it is write out the numerator and denominator. Numerator equals, oops, wrong brackets, square brackets. Then write the coefficients in the numerator. 2195, 129.8, 985, 2075, 286. So that's what I just did. I put the numerator coefficients up to S2, not the next ones, because it doesn't show there. You put in literally what you see, because we're modifying it. In the denominator, do the same. Oops, square brackets, sorry. 0.01, 1.539, 61.06, 472, 1483, 2075, and 286. Have we got that right? Yep. Okay. So there we go, numerator and denominator. Now I can write the modified version of figure 7 closed loop transfer function, and I'm going to call it fig7 CL mod, and it is open bracket, top of fraction, bottom of fraction, close bracket. The top of fraction is going to be the numerator, so that right there. So I'm actually going to replace these square brackets with NUM, and the bottom is going to be the denominator. Remove those and put DEN. That now is the transfer function, the modified transfer function, featuring the numerator and the denominator for step 6. That. Now what we have to do is step 7 and step 8 we do now. Step 7 wants us to display the step response plot, and step 8 wants us to do the Bode magnitude plot. So let's do those together. So LTI view, open bracket, what graph do you want? We want the step response graph. Which system do you want it for? This one here. Close bracket. Now we want the Bode magnitude graph, so LTI view, instead of step, right inside here, Bode mag of figure 7 CL mod. So those are the two things we want to display. Let's just put a percentage sign in front of the previous LTI views, okay, to make sure they don't display. Only these two will display. Just before we're about to click run, I noticed a mistake in figure 7 CL mod TF, this line here. That TF should be there. I think in the previous step it was like that without a TF, and these red lines showed up, which means it's not going to run. So just before we run it, make sure you put in TF. So just change that there, sorry about that. So now let's run this. We've got these two graphs that we want to display. There we go. We've got the graph for step 7 and we've got the graph for step 8. So just before we move on, let's just label these two and call that step 7. That's what we just did. Let's call this step 8. Right, now these two graphs. Get all your characteristics displaying. Click on them, click on the next one, and click on the next one. Right, just before we save it, if you notice the rise time, it's now 0.508, above the requirement of being below 0.5. The overshoot also is below 5%, is above 5%, which is beyond the requirements, and the settling time is also nearing the boundary as well, nearing 5 seconds. So this illustrates why in the next step we're going to need to design a notch filter, because the notch filter will minimize these and bring the graph back down to how it should be. So let's save this, print to figure, save, desktop, pictures, save this as step 7, click save, close that. Now for the one for step 8, get the values displaying, file, print to figure, save. If you're using a large monitor, then you might want to increase the fonts of these of those labels and stuff, because otherwise they'll be really small, and when you paste them in your report they're going to look really small, you won't be able to read them. So if you're using a large monitor, you might want to change the fonts before you click save. So this one, the bode diagram, this was for step 8, so let's save it as step 8. Make sure it's a picture file, and then click save. Okay, close that, close that. So we've now successfully completed step 7 and step 8. These ones right here. That was for the system without the notch filter, and we saw how the performance requirements were not satisfied. Now we're going to design a notch filter that will hopefully satisfy the requirements. The notch filter has a transfer function given here. This is the transfer function for a notch filter. There's some proof here which you should do by hand and then put it in your report. We're not going to go over that now. What we will do though is we will go over these steps here, step 9 to step 17. Okay, so for step 9, start by choosing 2 sets of values for C1, that's not a C, but let's call it C, C1, C2 and WN. Let's choose 2 combinations of values for that. So let's just write it here. Let's call C1 equals 1, C2 equals 2, C3 equals 1. You can choose any numbers, not C3, sorry, WN equals 1. You can choose any sets of numbers. We've just chosen those. What they want us to do now is to plot this function fs using these. So how do we do that? Remember, when we type in a function, transfer function, into MATLAB, we have to type in only the coefficients. So if you were to put in these numbers, 1 into there, the 2, put that into here, C2, put in this 1 from WN, put that into these, and there, what coefficients of S would you get? Well, for this set, you'd get 1 as your first coefficient on the top. The second coefficient would be 2, and the next coefficient would be 1. And on the bottom, the coefficients you'd get 1, 4, because you're putting that 2 in there, and 1. Those are the coefficients you'd get. So what we do is let's type that in. So now we're on step 9. So let me just make that clear that we're now doing step 9. So let's call the transfer function fs1. I'm putting the 1 there because we're going to do this again for another combination, another set. So fs1 equals a transfer function, open bracket, top of fraction, bottom of fraction, close brackets. Inside the top, remember we said that the top coefficients would be 1, 2 and 1 after you put them in. And we said the bottom coefficients likewise would be 1, 4 and 1 when you put them in. Sorry, spaces. 1, 4 and 1. Then choose another set. C1 equals something, I don't know, you can choose them yourself. C2 equals something, and WN equals something. Put those in to the equation just like we did. I'm not going to do it because it's kind of long. Well, it's not long, but it involves multiplication. And then type in TF, open bracket, top, bottom, close bracket, and then type in your coefficients into here. So choose some numbers, work out the coefficients, put the numbers into there. So FS will be something. For now, we're not going to do that one. Let's just stick with 1. But you'll do the same thing twice, basically. So Now that we've got that transfer function, step 9 wants us to generate the Bode magnitude plots for them. So remember how we do that? LTI view Bode mag of FS1. Close that. If you were to do the other one as well, which you should do in your own time, you'd put Bode magnitude graph of FS2 as well, but we're not doing that one, so let's just put that thing there. So this is the graph that we get for step 9, and that would be the second of the graphs that we would have got for step 9. So now let's run this. Before we run this, let's get rid of all the previous LTI views by putting percent signs in front of them. Then we can run it. There we go. So what we've got now, what this is the Bode diagram of a notch filter that has the transfer function FS1. The notch filter that has this transfer function when we've put in those values for those parameters. C1 we put in 1, Wn we put in 1, C2 we put in 2. Putting in those parameters, generating a transfer function for this notch filter. That is the graph you'd get for it. What do you need this for? You need this for the proof that you're going to do in step 9. Before you save it, just click on any random point because you're going to need it for the proof. So you're going to need these two numbers for the proof, the magnitude and the frequency. So let's just save that. Print to figure. Save. And let's call it 9A, because you're going to do it again for the FS2. Choose another set of parameters and do it again for FS2. By the way, make a note of which one was the magnitude and which one was the frequency over here, magnitude and frequency, because it doesn't seem to keep it once you make the picture, once you go to print to figure screen. So once you've done that, you've got that for 1, and then do that again for your other set, LTI view of FS2, calculate sum for FS2, and save that as 9B. Then what you've got to do is step 10, 11 and 12. What you have to do now is design a notch filter. You have to find values for C1, C2 and Wn to design a notch filter that will allow you to reduce the resonance of the graph of the system that we got in figure 7 a few steps ago. So in number 9 we chose some combination ourselves of C1, C2 and Wn. These steps here, they're going to allow us to get actual appropriate values, optimal values, an optimal combination of values that will allow us to make a notch filter to reduce the resonance. So let's start with step number 10. Step number 10 is saying, let's look at the graph that we had for the system without the notch filter and let's see what's wrong with it. That's what step 10 and 11 are asking us to do. So let's go to MATLAB. Where was the graph that we had? The graph that we had was this one here. Bode magnitude, step 8, and the response plot in step 7 for the system we had. So step 7 and step 8, those are the ones. Use the LTI viewer to obtain the Bode magnitude, so that was step 8. Step 8 from the previous system. So let's go back to step 8's one copy that thing that we had, because it's asking us to again generate that graph. Just before we do that, let's put a % in front of other stuff so it doesn't display, and let's label this as step 10. Let's go. Okay, nice. We've got it generated. Now what does it ask us to do? From the Bode magnitude plot, obtain the resonance frequency WR and magnitude MR of the resonance peak. How do we do that? Right click, go to peak response. This is the peak, the resonance peak. Click there, and there you go. We've got MR 0.442 and WR 1.18. Let's write those down. MR equals 0.442, WR 1.18. Still recording? Yep. 1.18. So there we go. MR and WR of the resonance peak. Now we've got to define gamma and delta as these. So let's do that on a calculator. Okay, so using a calculator, I worked out gamma and delta using these two equations, using MR. Used a calculator and I worked out gamma is this, 0.95039. Delta is 0.96501. And so that's step 11 completed. So now that step 11 has been completed, from the Bode magnitude plot of the closed loop system, obtain the frequency at which the magnitude equals 0.7 MR. So what's that? So that graph that we just had open, the graph from step 10, let's just get it open again. This one here. We had the peak response, it was already displayed. That's what we used. So now it's telling us find the frequency where the magnitude is 0.7 MR. So just click anywhere. 0.7 MR, we've got to work out what is 0.7 MR. So MR is that 0.442. So in a calculator, let me just quickly put that in. 0.442 times 0.7, and the answer is 0.309. So I have to drag this thing along. So I just clicked on a point on the graph and this came up, and now I'm dragging it. I'm dragging it to try and find 0.309. That seems to be the closest I can get it. That seems to be the closest I can get it. 0.306, close enough. So the frequency at that point is 1.75. So we can put that in. Let's just type that in. W naught equals 1.75. Okay, and that means we've just completed step 12. Step 13 now is saying now we can work out the parameters, the optimal parameters to use for our notch filter, and these are given by these three equations here. So now we can calculate these parameters using these equations, and these equations feature all the values we've just calculated, like delta, like WR. So we can use these using a calculator, work out what WN is, what is C1, what is C2. Okay, so I'm just going to do that now on a calculator. Okay, I've just calculated WN using a calculator. Well, no, WN was right here, equals WR. So WN didn't need any calculations. 1.18. I calculated C2 though. C2 I calculated as being 0.63363 equal sign, and C1 I calculated as 0.60219. Okay, so now that I've calculated those, I can now move on to the next part. I can call this, I can define this as a notch filter using these three parameters that I've just found and give it an appropriate name. So let's call it notch TF equals open bracket, equals TF, then open bracket, top of the fraction, bottom of the fraction. So what goes in the top and what goes in the bottom? Go back to the equation for a notch filter, that there, and you put in the coefficients now. So the coefficient of the first one is just 1, and then the coefficient is that 2C1 Wn, then the next coefficient is Wn squared, and so on and so forth. So I'm just going to quickly type that in. And now the bottom. Okay, so there we go, the coefficients of the top and the bottom. So that is the notch filter's transfer function, and it will now use these three parameters that we've just worked out through the steps in number 10, 11 and 12. So that is step 13 complete. So now what do we have to do? Now it's saying put the notch filter in series with the system. So the system before had no notch filter. We saw the effects, the resonance in the system. Now we're going to put the notch filter, fs, in series with it. So we're going to use the command series in MATLAB. So let's call the final transfer function, let's call it final CL, equals series, use the series command, open bracket, and what is in series? The notch filter is in series with the original system. So what was the original system? Let's try and find it in here. There we go. It was called Fig7CL mod. Fig7CL mod. So that is now in series. And that was step 14. So that's now in series. You do not need to record a transfer function for this, okay? Step 15 and 16 are now saying to save the Bode magnitude and the step response plots for this final system, and to compare it with the original system. So basically what we have to do, we have to generate a Bode magnitude plot of the original system alongside the system with the notch filter. Then we have to do the same for a step response plot, once without a notch filter and once with a notch filter. So let's go ahead and do that. We want to view the Bode magnitude plot of which two systems? We want to view the Bode magnitude plot of the original system, which is this, alongside the final system that includes the notch filter. Then we want to do the same for a step response plot. So that was number 15, and that is number 16. Now let's quickly get rid of all the other LTI views so we only get to see these two graphs. Hopefully when I click run, the two graphs will be displayed on the same axis. I forgot times. Let's try that again. And there we go. This is the step response plot, and this is the Bode diagram. The blue line represents before, without the step, without the filter, notch filter, and the red line represents after. So now all you have to do, get ready to save this stuff. Let's get the peak response up. How should we do this? Let's get that there and there. There, like this. Okay, and you can use this in your discussion section to describe how the peak gain was reduced, etc., etc. So let's save that. Save desktop, and what number was this? 15. Save. Can close that now. Close this. Now for the other graph, the same thing. Peak response, settling time. Now let's keep an eye out and see whether the requirements are met, whether this is within the requirements or not. So that's final CL, and that's for fig mod. Oh, it's hard to click, one's on top of the other. Come on. Oh well, you can click it on your own. Right, let's have a look. Oh, there we go. It's here. So has it satisfied any of the criteria? It looks like it's brought the rise time up. It's brought the rise time up, so that hasn't helped. The overshoot, it's definitely brought it down, but it's still kind of outside the 5% limit. And the settling time seems to have increased. So you can say it's kind of partially successful, I guess. It did bring one of them down, but the other two it wasn't as successful. In the discussion you can mention all this stuff. Each time I do it, it seems to be different. My personal one for my coursework was much more successful than this. It satisfied 2 of the criteria and only 1 was left unsatisfied. This one seems to have made 1 better and the other 2 worse. Anyway, call this 16. And there we go. We now have all of these graphs and that transfer function that they asked us to save, everything in bold. We now have them for use in our coursework. And that's it.